Welcome to Transfer of Bioprocess Engineering Week 2. So, the continuation of aspects of rheology in bioprocess engineering. Last class we discussed about the non-tuning fluids, how it works with respect to shear rate. But here, what is the time dependent viscosity in non-tuning fluids? Because the previous one just we discussed only non-tuning fluids and how the shear rate works here. But in this case, in certain non-tuning fluids, the apparent viscosity, we always discuss the mu A apparent viscosity is not only function of shear rate and again the function of time also. That's only here we are adding here. It's not only function of shear rate, it's a function of time also. That's only we mentioned here. It's a time dependent viscosity. Okay. So, there is a two cases there. One is a steady state. I think every class we always discuss these two, steady state and then unsteady state. Unsteady state, steady state and unsteady state. Steady state is the time independent. There is no time independent, but whenever unsteady state, that is a time dependent. So, this problem all time dependent because this is all unsteady state. So, such a behavior we always say as a time dependent rheology, and then again shear rate also play here. So, the viscosity evaluation occurs due to the microstructural rearrangements within the fluid of during deformation. So, what are the fundamental characteristics here that we will discuss here? Apparent viscosity changes at a constant shear rate. The apparent viscosity mu A, okay, always the changes with the shear rate. Then other one is for the reflect non-instantaneous responses of internal structure to applied stress. Then distinct from shear rate dependent, that's called a time independent. Time independent non-tuning figure also behavior. Of course, we need the transient rheological measurement for proper characterization. These are the fundamental characteristics for non-tuning fluids here. So, there is a two type of this one here. One is the rheofectic fluids, that's called time dependent shear thickening. Already we discussed the non-tuning, there is shear thickening, then shear thinning, many we discuss here. One is the pseudoplastics, then other one is for dilatant. So many examples we discussed in the previous classes, and this one is called rheofectic fluids, but it's a time dependent shear thickening. So, what is here the viscosity, the apparent viscosity same way apparent viscosity increases with time at constant shear rate. We always write the shear rate or the constant shear rate. So, definitely it's associated with the structure formation, then aggregation under the shear rate. So, rheofective behavior is rare in bioprocess system. Normally, in the bioprocess system, it's a very difficult to see the rheofectic fluids here. But anyway, certain examples are here. The typical example for non-bioprocess here, we have to give here certain gypsum suspensions. So, the calcium sulfate, gypsum suspensions, then highly concentrated inorganic dispersion. These all come with the non-bioprocess example for the rheofecting. Sometimes bioprocess relevance here, so there is a limited practical importance here, the rheofectic fluids here, but they rarely observed in the fermentation broths or biological fluids. That what we discuss same way, because it's a time dependent also, then shear rate altogether very difficult to see in the non-bioprocess problem, but most of the chemical problems, all the type of very simple problem, we can always see this one, the rheofectic fluids here. So, other one is for thixotrophic fluids. This is always we can discuss in the bio problem, because it's always in the bioprocess problem always available here, the examples also. Then here the apparent viscosity, the mu A, the apparent viscosity mu A decreases when increase the shear rate, okay, or constant shear rate, then with respect to time. So, the same what we discussed already also, but the previous one we never bother about the time dependent, but here we added as a time dependent one of the another variable. There is only one variable, but here two variable. One is the time is one variable, then other one is the shear rate. Shear rate is the another variable. So here the stretches break down progressively under the shear rate. Whenever if apply shear, this slowly the breaks down progressively here. So then completely upon removal of stretcher, say example you are giving some shear rate and then it goes like A gives something. For a simple example, A gives B. When you apply something, then it goes to B, then again back to here. So it's like irreversible. It's not like irreversible. It's a reversible behavior. So when you apply the shear rate, it moves to one to other one. When you remove the shear rate, then again go back to the same position. So that's only upon removal of shear on the stretcher partially, or sometime we can fully recover as it is also. That's called a reversible behavior, what we discuss here. So then microstructural origin of thixotrophy. So here that's a reversible breakdown or rebuilding internal structure, such like the same thing what we discuss here. Then the mechanism, what are the mechanism include here? The orientation of elongated cell or mycelia. Then alignment of extracellular polymer chains, that is another mechanism here. Then the disruption of weak intermolecular or intracellular networks. So time required to reach equilibrium between here, say example stretcher is breakdown first when you apply a shear rate, then again when you remove the shear rate, then the stretcher is redevelopment. So it's a reversible, it's called a reversible process, but the previous one is, this is called a shear thinning, but the shear thickening, the previous one, no, rheophyctic fluids. That is not a reversible, that's irreversible, because once you go to that one, we cannot do that one, but this is a shear thinning. It's always reversible when we do the process here. So thixotrophic fluids, then time dependent shear thinning, what we discuss here. So we need some example. So whatever we discussed already in the previous class also we discussed the filamentous fungal fermentation. So that's called Aspergillus, Penicillium, all come in the thixotrophic, the bioprocess. Then culture producing extracellular polysaccharides. Example xanthan gum, this all comes in the thixotrophic bioprocess. Then mycelial pellet forming microbial system also the best example for the thixotrophic in bioprocess. So the practical observation, the broth appears highly viscous whenever there is no shear rate and the viscous is a very highly at a rest. But whenever if you during agitation or pumping, if you do agitation or pumping, then automatically the viscosity drops. If shear rate is absent, then automatically the viscosity gets increased. That's only when it's rest, the broth appears highly viscous, and whenever if you agitation or pumping, the viscosity slowly decreases. What are the rheological hysteresis here? The thixotrophic fluids exhibit the hysteresis loops in the flow curve, the first point. Then upward and downward the shear rate sweeps but don't coincide, that one. Of course, this indicates time dependent structural evaluation, that one. So the another one is for, it's a very important diagnostic tool in the rheometry for studies. So we discussed time dependent shear thickening, the previous one, and then again we discussed here time dependent shear thinning, that we call it the thixotrophic fluids here. So what are the engineering implication in bioprocess? So here the time dependent viscosity, influences here. What are the influence here? Of course, the power consumption in the bioreactor. So we always discuss the power consumption in the bioreactor, definitely it gets the influence, because we need more thorough knowledge how the viscosity, whether it's a Newtonian or non-Newtonian fluids, or how this one. Then again, we need definitely it will influence the mixing efficiency, then circulation pattern also. The circulation pattern, how that one, then the mixing efficiency of that one. So the last one is for what are things are here, oxygen and the nutrient mass transfer rate. Oxygen, nutrient, both definitely the mass transfer. We will discuss more on how the mass transfer, what are the diffusion, the dispersion, then convective mass transfer, all we will discuss the forthcoming classes. So, we will get thorough knowledge here. So, during startup, when you start, the viscosity looks very high because there is a poor mixing. When you start the operation, when you start the bioprocess, it looks like the viscosity is very high. When you pour mixing also, because there is no agitation, there is no shear rate. But when you increase the shear rate, then the viscosity apparent viscosity get reduced, but the transfer properties will improve here. So, that is the engineering implication in the bioprocess, how this, the time dependent viscosity, what are the influences, then during startup how this behave, then for during steady operation how this one. So, what are the key here, the difference here, and then shear dependent and then time dependent behavior. So, we discussed previous one pseudoplastic that shear rate is, but there is that depends on time is no, because that is called a pseudoplastic, and we discuss also some examples. So, many polymer solutions will come under the category of this one, the pseudoplastics. But the thixotrophic depend on shear rate, yes, but the time also we are counted, that is called the thixotrophic. The best example for fungal fermentation broths. Rheophytic, but already we discussed, it is a rare in bioprocessing process. So, only inorganic suspension, we can always non-bioprocess, only we can discuss the rheopectic here. Of course, here what is the shear rate? Yes, shear rate also dependent, then dependent on time, yeah, dependent on time also there, and then shear rate also there, that is called rheopectic here. So, what are the key takeaway points from here? Of course, we discussed here time dependent viscosity definitely reflects the dynamic microstructural evaluation here. So, thixotrophic is a commonly many of biological process commonly involves the biologically active system. You need proper understanding is essential for the reliable transport analysis. What are the reliable transport analysis? Then accurate bioreactor operation. So, how the bioreactor operation is accurate. Then industrial scale bioprocess optimization. So, definitely when you want to do industrial scale, the batch to industrial scale, definitely we need bioprocess optimization, because how the batch works same way not possible for when you make industrial scale, because some parameters we never use in the batch, but some parameters we always use in the industrial scale. But commonly example some like 4 to 5 parameters, you can take 1 or 2 parameters or maximum 3 parameters to use to develop the industrial scale. So, that is the difference between the batch and this one. Whenever optimization, this is here different, but here different, we never use the all variable the batch to here, but 70% or 60% of variable we always use the batch, whatever the batch optimization of variable to industrial scale problem. So, this is a famous this equation, that is called power law equation. Okay. So, here the tau equal to k of du by dy n, already we discussed here. So, many fermentation industries definitely it should go with this equation. So, this is called a power law equation, already we discussed, this is a power law equation. So, here the k is a constant proportionality. Say example is already proportional is there, then there is no k. You want to remove, then you have to add k. Okay. The k is the constant proportionality, what we already discussed here. So, the same problem, if it goes n equal to 1, then it behave as a Newtonian fluids. Already we discussed n equal to 1, it behaves as a Newtonian fluids. Whenever n equal to less than 1 or n equal to greater than 1, then this behaves as a non-Newtonian fluids. So, here again the Newton equation k equal to m, or sometimes they say mu, that is viscosity. We always say Newtonian fluids here, then non-Newtonian fluids for if n equal to less than 1, because so far we discussed only this one, what will happen if n equal to less than 1, n equal to greater than 1 here. So, here what are the usually Newtonian here, the rheology of dilute broth, then culture of yeast, the non-chain forming bacteria, it's always come under the Newtonian, this one. Most of the mycelial suspensions have been coming is the pseudoplastic. If there is yield stress is there, then it will always come as a Bingham plastic. I think you already we discussed very thoroughly what is pseudoplastics, what is Bingham plastics. Okay, that's the same thing here. Then when the fermentation produces the extracellular polymers such as the microbial production of xanthan. So the rheological characteristics of broth only depend strongly the properties and the concentration of these materials. So that's only they want to mention here. So the rheology of fermentation broth often changes in the batch culture, throughout the batch culture. What do you mean here? The changes, sometimes it goes to Newtonian behavior, sometimes non-Newtonian behavior. So definitely the rheology will change. It's not like only you can say only this one. So definitely will change that throughout the batch culture. So same way here, broth obeying the power law, the flow behavior index we solve, let's say N, flow behavior index N, then other one is the consistency index K. The flow behavior index N is a dimensionless, there is no dimension, but here K always there is a dimension is there, can vary substantially the culture time. Okay, that's only we mentioned all here. So simple the example how this one behave here. One is a flow behavior index, you just okay versus time here. It starts in terms of hour. It starts 0 to 150 hour, and then the other side is a flow behavior index here. So here how the changes N and K during the batch culture of endomyces here. So this is an example of how endomyces fermentation happening here. So first you assume as a Newtonian we assume as a N equal to 1, N equal to 1 Newtonian. So here N equal to 1 is starting, then is coming as a pseudoplastic. You just see here whenever the time increase here, so then it behave as a pseudoplastics. But after some time again it goes to, it try to go the other way. But we already discussed, no, it's always changes the viscosity here. So this is a flow behavior index, we call the flow behavior index here, that is N. N is a dimensionless, so because that's the only number, N 1, 2, 3 or less than 1, whatever here. Same way for consistency index here, K, the units are here, okay. But that's if it gets okay increase, the K increase with respect to time, it's getting increase suddenly, it's always it goes the, you can see this is steadily throughout the most of the batch periods. So around 100 hour, it's always is the increasing states only. So we can always say the mu A, the apparent viscosity, the proportional to K is always getting increase here. The best example for variation of rheological properties in endomyces fermentation. What are the changes in rheology fermentation broth are caused by? Definitely the cell concentration is main factor, how the cell concentration behave here. Then the cell morphology, next one. Then osmotic pressure of suspending fluid, this one. Then next is the concentration of polymeric substrate. Then the final is the concentration of polymeric product. These are definitely the changes in the rheology of the fermentation broth. We will discuss one by one how this one, the cell concentration, the suspension of Newtonian liquids, so is Van equation. So here mu equal to mu L 1 plus of 2.5 we called a pi, then 2.5 plus 7.25 of pi square. So here the mu L is the viscosity of suspending liquid, the mu L is the viscosity of suspending liquid here. The other variable here that we called as a volume of fraction of solids. So the same above equation has been found to hold for yeast the spore suspensions up to 14% of volume of solids. So, but the same similar results have been found for the mold pellets in the liquid culture also, we can find the same type of results. So, what you want here, the final here, when viscosity is strongly depend on the cell concentration, because that is a very important. The viscosity is the mu is the strongly depend on the concentration of cell concentration. Okay, the cell concentration here. A steep drop in viscosity, if you want get steep drop in viscosity, only can be achieved by either you have to dilute the broth with water or the medium. So, either you dilute the broth in water with water or in the medium, so that the viscosity can sharply get decrease, or it is not possible. Or other one, what we can do, we can remove the periodically the removal of the pot of culture or refilling with the fresh medium, so that they reduce the viscosity and improve the flow of the fluid flow in the viscous fermentation. These are the cell concentration what we discuss here. So, other one is the cell morphology. How the morphological, first one discussed cell concentration, and then this point is cell morphology. The morphological character is how its influence in the broth rheology. So, here you just see the dispersed filamentous growth produce a structure in the broth. It is a result towards to pseudoplasticity and yield stress behavior, or both also will here. On the other hand, what we can discuss here, the same thing, the broth containing pelleted cell tends to be more Newtonian behavior, depending on how the readily the pellets are deformed during flow. So, the extent of branching of hyphal cells can also affect the rheology. The cells here, the cells with the high branching frequency are generally the less flexible than non-branching cell, of course, they produce a higher viscosity. So, what we got here, the pelleted mycelia are more closely Newtonian behavior. What we discuss same thing is the behave as a Newtonian behavior than the filamentous cell, So, that is why we discuss in the graph now. So, the flow behavior index N for the pellet is very closer to unity, because whenever the flow is a behavior, of course, it is already behave as a Newtonian behavior. If Newtonian behavior, automatically the N close to 1 or very approximately 1, that is only they are discussing here. So, as indicated figure, another we will discuss the next figure. The consistency index and apparent viscosity can differ by several order of magnitude depending on cell morphology. If its cell morphology is different, and definitely the apparent viscosity also will vary. That is only we discussed all this point here. These are the graph. So, there is a cell concentration, x axis gram per liter, then the flow behavior index is N. So, we took this one, we gave the reference also here. What are the reference here? You can get the reference also. So, here the flow behavior index N1 behave as a Newtonian fluids. Whenever N less than 1, close to this one, that behave as a non-Newtonian fluids here. So, here two cases we are seeing here, one is the filamentous mycelia, other one is the pelleted mycelia. So, pelleted mycelia, how this behaves here, initially it behaves as a Newtonian. Once the cell concentration increases, the cell concentration increases, and then slowly it goes to non-Newtonian this one. That is only whenever concentration increases. So, it is a 10, 20, then 30 gram per liter, the values are totally different. The N values here, corresponding N values are 0.5. Same way here, it starts with the N around 0.7 and behaves as a non-Newtonian. When you increase the cell concentration, then is the slowly flow behavior N value also getting decrease. But now we discussed about how the cell concentration versus the flow behavior index. Same way here, the cell concentration gram per liter is here, how the consistency index K value. So, N is there is no unit, that is a dimensionless, but dimension factor here. how it behaves when it 5 grams, same way cell concentration in the x-axis, then y-axis consistency index here, then the cell concentration get increase, the filamentous also get increase. You can see here filamentous mycelia. Same way here pelleted mycelia, one if it get around 20 the concentration, though it gets increase, it's very steep get increase. So, concentration index here get increase. That is only difference of how the cell concentration with respect to here what we discuss cell concentration, how the vary versus with the flow behavior index n and then k in this problem. So, the next one is for we discussed totally 5 points now. So, the cell concentration, then cell morphology, how the product and substrate concentration. So, when the product fermentation is a polymer, using polymer, in the batch culture rises the broth viscosity. Okay, that is only. For example, another example for exopolysaccharide, the viscosity measured at the shear rate is 1 second inverse, even can reach as a 24,000 centipoise. This much high it goes to at shear rate 1 second, this one. So, cell concentration normally negligibly affect in overall viscosity in the fermentation. In the rheological property of fluids are dominant by the dissolved polymers. That is what we discuss here. And then other the producer having a similar effect of the culture rheology, that includes alginate, xanthan gum, all this one, the product and substrate concentration. Next is in contrast, when the fermentation medium contain the polymeric substrate such as a starch, already discussed same thing, the apparent viscosity mu A will decrease when the fermentation progress, and at the same time the polymer is also broken down. The polymer gets broken down, the viscosity also will get decrease. The apparent viscosity will decrease when the polymer chain is whatever the polymer gets broken down. And there also could be progressive change from non-Newtonian behavior to Newtonian behavior. That is called, this is a n less than 1. So, it moves to n close to 1. That is the Newtonian behavior here. The mycelial fermentation, the changes normally usually start the mycelial, the fermentation very short, the cell grows and develop a structured filamentous network, in the broth becomes increasingly pseudoplastics and then viscous here. So, the less nostril, the osmotic pressure also the culture medium affect the cell Durger pressure. This in terms of affects the hyphal flexibility of the filamentous cell. So, when you increase the osmotic pressure, when you get a osmotic pressure get increase, it gives a lower Durger pressure, making the hyphae more flexible. So, the improved hyphal flexibility reduce the broth viscosity, the viscosity get reduced and also have a marked effect of the yield stress. Thank you.